Good man, good man.
So far, yes.
Just checking to see if he's awake.
So far, yes. I know it's over.
Hello and welcome, viewers, to the history of math. We'll get it together one of these days. All right, Adrian.
Take it away.
Yep.
Here, I'm going to hand this to Tim before I start.
Shut up. Oh.
Oh, I was like, I looked over on the shelf and I was like, there, there we go. Critical line. We're taking it away. No intro to, we're doing history of math.
I already said that.
Okay, I wasn't listening. Apparently,
Never is.
I don't listen very well.
No one ever does.
So last time what we were doing was trying to not say so much. So I just said it 4 times in the last 30 seconds. That's how that goes. You can't, I am's who I am's. What we were doing last time was going through the history of math and we ended up at Egypt. And I was going to do, actually no, last time I didn't do it. So then I was going to do Babylon and the Plimpton 322 tablet. And then I had a life crisis and I had to give a cat away. And so we didn't do that one. That's why I was like, why do I have one missing in my head? So we'll do that one and we'll squeeze that one in later and we'll put it in chronologically. It won't be right, but it's like the prequels and the Star Wars ones. It's like, why is it 1, 2, 4, 5, 6, 1, 2, 3? Because I forgot to do a couple. Life happens. So we'll squeeze in the Plimpton 322 tablet. I've got 2 of them right here. And then that was on trigonometry and ratios and triangles. I also wanted to do, we'll see what we do today. Can we split it into pieces now that I think about, I'll do Egypt and then I'll freeze for a little bit like this. You're like, you don't have to do that. And then that'll be the place where I cut it. And then we'll talk about, I also wanted to just talk about arbitrarily geometric ratios and where we get different kinds of numbers from and how we get algebraic rules, like somebody in the coffee line and she was wearing assholes live forever on her pants and I was like, that's why I'm one. And then we started talking because she's in my class and then she said, how do you know that, or how did they come to the conclusion that this was true, the algebraic operations when we do this is called distribution property, how do you know this? And I was like, oh, that's exciting. So it's geometry. It's geometry, not algebra. So after I do the Egyptian pieces to keep the show on the road, because I let it derail a couple weeks ago, I also want to do a bunch of algebra from geometry and start drawing pictures, start drawing pictures, start drawing
Yes, we
pictures.
could do it. So to answer that question, yes, we can
Yes.
do however we can bring it up however you like.
So from the Egyptian math, and again, what I was going to do is we're sort of, if you've met us before, we're half organized or 2/3 organized. 2/3 will be a pun because the Egyptians really like 2/3 and 1/3, which becomes unity. And they wanted what they're going to call special fraction decompositions of certain numbers. And so let me drink some coffee. And then my point being is I have a lot of problems. And when I started investigating, I have a lot of books on history and a lot of books on different eras and different cultures and their early mathematics. So the first time around, I'll do a few problems on each, and then if you want, I'm going to start giving you problems similar to the ones that I do, and then we can talk about it again and revisit it and do the whole series all over again in a couple of years and just add the things that I didn't talk about the first time in the second time. And then that way I don't have to spend a million years on the Greeks like I did when I taught Lorenzo the history of math
Hey,
the
that was
first time.
great. I mean, that could be a
We learned a lot about the Greeks, but then it's like, and then the rest of the world. So the major things I wanted to do was starting to do now that we have representation of numbers, doing a little bit of arithmetic and algebra in amongst those numbers and trying to get formulas or good ways of computing things within the numbers. I'm trying to remember what the clever name they called the unit fractions. I was like, that should have been obvious. So they really like 2/3, and then what they're going to call a unit fraction is 1 over n. And then this gave unity. And so for the most part, what they're going to be trying to do is they're going to try and decompose numbers into or they're going to, the whole numbers they were okay with because there wasn't a repeating part. And the problem, I think what they're seeing with this is the, and then all the other, all these 1 over n's, they're going to try and turn into unit fractions especially. And so 2/3 is, if I use long division, a bunch of sixes repeating, and I could write it as 0.6 repeating. But if I use numbers that have 2 or a 5 in them, and if I'm using base 10, then they're going to truncate, and then they would have infinite numbers which didn't repeat, because if you look at 5 over 2 for some reason, whatever you're doing, if I have 2.5 things, then this becomes 2.5. And then the zeros are the things that are infinite repeating. So it does have this, but this is the type of number we call a truncated fraction. I can't spell truncated. And I think that that's early on what was bothering people, was the fact that some of the numbers, even the rational ones that have an infinite repeating pattern, they wanted to find more the ones that had an infinite non-repeating pattern, or not infinite non-repeating, those are the irrationals, but they wanted one where it was seemingly truncated and it didn't have a repeating pattern, or it was just the zeros, so they could write it down as a nice sum of fractions. But they kept 2/3, and it got a mystical notion attached to it, because 2/3 was the one thing that they used that would fill in all the gaps, I think. And then for some reason they kept 2/3, but everything else they tried to write as 1 over n's is what they're trying to do, 1 over n's. And they call this a unit fraction. Now let's see how to do that cleverly. Is that the first thing I'm going to do? Yes, okay. I was like, shit, is that in the right order? Then I'll do the heap problems, where they would just heap things together. So as I do this, you can speed. No, where is this? Oh, I was like, where's the table that I did this on? And it's in my hand. It's in my hand. I did it ahead of time. So the first time I taught it, you can also see how I did this. You can't see my notes that I'm looking at on the screen, but in the notes before I did this, the night before I would go teach Lorenzo, I would do all the computations, and then I would put it in the lecture notes, and then I would pose the problems to them right after I made sure that I could solve them. If there was one that I couldn't solve, you sweep it under the rug and you go, what are we going to do without the solutions? Just like in The Simpsons. So I didn't give you those ones because I couldn't figure it out in the night that I had, the time that I had to do it. Because when Karen Burrow said, can you teach the history of math? I was like, yeah, I can. And in my mind, I was like, I have no idea what we're going to do in that class. But yes, I'll take your money. Yes, I'll take your money. So one of the first problems is, I'm going to do one, and then I'm going to give you the homework problem. So if you want to type this one out, this is the problem I'm going to pose to the people. And then I'll show you, hopefully, you'll understand that use whatever I talked about in this video to try and help you solve the problem I'm about to give you. But here's the problem before I talk about that cleverly. Here's the real world problem that they had and why they started thinking as mathematicians. These are just day-to-day commerce people, and they want to know how to share loaves of bread. So to build the pyramids of Giza, the army marches on its stomach. So what they're trying to do is, that wasn't very square, but they're using a square-based pyramids. And to do this, they have a whole lot of, we don't know at this time, let's call them workers without compensation. Slaves. That's from Ragnarok, Thor Ragnarok. He's like, I don't like that word slave. He's like, workers without compensation? Or he says something like that. It's like, double speak. Don't make it sound nicer. They're still being used and abused. But all these workers on the Egyptian pyramids, they have to run on bread. So they have to share bread. And then they're making loaves of bread in the ovens, and then they're bringing them to the people, and then they have to share. So here's one of the first problems they realized. How can 3 loaves of bread be shared with 5 people? I'll give you the small one, and I'll do, because I like to do the hard ones, and then you apply that and steal the idea from me. It's not the numbers or whatever, but the bigger the numbers are get, the harder the problem might possibly be. So I have 3 loaves of bread shared equally. I have to get my English sentence to make English sentence sense. English sentence to be shared between. Oh, also shared. Everybody wants this one equally. It's like, you get none. These guys get this much. Done. It's like, well, that's not really what we meant by shared. Shared equally between 5 people. So there's some numbers in there, and notice that I didn't use any of the symbols. I used the first avatar of numbers, which is the word that I have for them, 3 and 5. And so this is the problem that we're going to do. What I'm going to do instead is now go through some theory, and I'll change mine to all we have to do you see now? Once you have a problem and you phrase it, then I get the structure of the mathematics, and then from my point of view, all we're doing is changing the numbers. So 9, that was what the Egyptians would use between 10 people. So that's the one I'll do. And then you try and give me the homework. I don't know how we're going to do this. Put this on our website or something like this. Give us the answers. I'll figure out eventually.
Yeah, we'll have a way for it. Or Discord. Yeah, there we go. Put it on our Discord. A picture of it on the Discord.
Right. I knew I'd figure it out eventually. So let's see how they're doing this and how they're going to break them up. Before I did that, one of the problems was representing all the numbers n over 2 and, what was it, n over 10 as unit fractions, I believe is what they want. And for some reason, sorry, I wrote that upside down, 2 over n. 2 over n. And so what they want in this table is they want to have, and yes, they wanted to use the fact that, just wait. Yes. Obviously, they want to write this as unit fractions, but they want them to be distinct unit fractions. So I can write this as 1 over n plus 1 over n, but those are not distinct. So instead, what they figure out is this, and I'll give you the formula ahead of time, and then we can ponder how they got this. But I can write 2 over n. It has to do with the fact that 6 is perfect, and 6 sums to 2, and then you can multiply both sides by n. But I'll show you, I'll leave you ponder. I just said it, but I'll leave you ponder. This is 1 over n plus 1 over 2n plus 1 over 3n plus 1 over 6n. And so what you can also ponder to yourself, because we're already doing this, is how did they get this equality? And this has to do with, I'll give you a hint, perfect numbers. And 6 is perfect. I made you do that on your homework. I didn't phrase it specifically, but the sum of all of the divisors, the reciprocals of the divisors of a perfect number equals 2. Or I said it in rhetoric. You can see the power of algebra because I didn't write it down. So if you could say, I'll say it one more time. The sum of the reciprocals, I just want to do it now. Can I just do it? I was like, I want to leave it for homework. This is the problem I have. It's like, I want to do your homework though. It's like, this is how I knew I was going to be a math teacher eventually. It's because like, I don't even want to let you waste your time trying to find it. I want to do it right now. 6 is perfect. What does that mean? It's 1 times 2 times 3, but it's also equal to the sum of its proper divisors, 1 plus 2 plus 3. And now if I take these, you can magically show me, but it works for all of them. 2 is equal to the sum of the reciprocals of all the divisors, not just the proper divisors of the perfect number. So what are the divisors of 6? 1, 2, 3, 6. These are the proper divisors. 6 is not proper. But if I now take 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 6, do you see? They had this magic perfect number. And that works for any perfect number. The next perfect number is 28, and then 496, and then 8128, and then it goes into the millions really fast. But these are the first 4 perfect numbers. And what that means is they are the sum of their proper divisors. And then if you take the reciprocals of all of their divisors, including the number itself, you always get 2. And now do you see how they went from this one to this one? They just multiplied both sides by 1 over n. And then you get 2 over n is n, 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 n. So that's how they're getting this. They use the perfect number, and then they notice that any number 2 over n, they can write as unit fractions, a bunch of distinct unit fractions. So they didn't want to just use 2 distinct unit fractions. That was cheating, I guess. They wanted to see from all the 2 over n's how to get as many distinct unit fractions as they could get. And so there. I should have left it for you, but I'm driving, so there's your introduction to. We're going to go through that when we get to the Greeks. We're going to do perfect numbers in its gory detail, and we'll talk about Mersenne numbers and Mersenne primes producing perfect numbers and how to generate them. And the fact that there's an open problem, if you want right now, open problem in math. Problem. I almost wrote problem.
Your English is perfect
Yeah,
today.
yeah. It's flawless. There'll be mistakes in my English and my math. That's the thing. We just want to correct them constantly. You know what I was going to say. Did I have to say it exactly correctly? No, not really. So the open problem is or are there is there any is there any odd I'm leaving it. Odd perfect numbers. You know what I meant. And I can't see what they're saying in the chat because I have my notes above me, but they're probably saying funny. Yes. Yes, I am. Are we English letting you down? Yes, it's me perfect English. Me perfect numbers, no perfect English. All right, so let's do this. So what the first says is, can you take the numbers from 1 to 10 and write them all over n is what they wanted. So do I have enough here? No, I don't. Let's make them smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9 is what I wanted. And so now can we draw all of the numbers? Oh, also, where was that clever calculation I had that I'm stealing from myself? I wrote all these things out and then I couldn't remember how the hell I did any of them. So then I had to remind myself. Where did it go? Edit all this out. No. Is that it? No, that's not it. Oh, that's the one I wanted for a different one. Oh, there it is. I'm cheating. The Oilers played last night and it's Sunday morning. It's not the morning anymore. To get these ones, I can get from this one. If you notice that n over 10 is equal to n over 2 times 5. And so I can write this as 1 over 5 n over 2, which is what? The 2 over n I can write as, this is 1 over 5 times 1 over 2 over n. So I can get this table, half of the table, for free by doing the first half of the table. I should point that out also, which I have pointed out to myself at some point. Now I'm just going to cheat and list them off quickly for you. So for the first number, what do we get? For the number 1, why did I write 2 there? Oh, because that makes sense. Okay. Because that's equality means equality. So for 2 over 1, we get 2. I'm like, why did I write 2 there? Just a second. Let me do the calculation in my head. I'll get there. Whew. Starting to... It's getting hot in here. Oh, no, I can't take that off. Lapel mic. That's for my OF later. I forgot. I'm getting extremes confused. Okay, that was a joke. Jokes, people. The next one's an integer too. The next one's an integer. So I keep moving, duck and move. So we're going to do 2 over 2. This is a 1. Good. And we can write the integer as unit fractions if we want, but we'll do that. This is this magic one. They didn't change it at all, so that's 2/3 I'm squeezing in there. That's the special one. So they didn't try to manipulate him into a unit fractions. And then 2 over 4 we can do as, which is going to reduce to 1/2, which you could write as 1 over 4 plus 1 over 4 if you're going to be lazy. And then we have different decompositions. 2 over 5 immediately. Now what we're going to do is I want to write 2 over 4 as these unit fractions. So that's what's happening here. I'm going to write it as is equal to 1 over 5 plus 1 over 10 plus 1 over 15 plus 1 over 20. Notice that's, you'll see, you can try on your own to see how I'm just going to give you the answers, I guess, and you try to see how and spend some time with it if you really want how to actually create these fractions. And so this one, 2 over 6 is going to be 1/3, but we can still write that as 1 over 6 plus 1 over 12 plus, my board isn't, my line here isn't big enough. Oh, that's a good noise. Let's move that slightly. 1 over 12 plus 1 over 18 plus 1 over 36. And then 2 over 7, we can do the same way. I'm probably just using this formula. 2 over 7 is going to be, oh, this one you can start seeing is 1 over 7 plus 1 over 14 plus 1 over 21 plus 1 over 42. And then the last one's 2 over 8 reduces. 2 over 8 is 1 over 4, which I can write as 1 over. They didn't write it as the reduction of the number either. I'm not sure whether they were aware of this, but they still wanted to. I think they're doing real world. So they're dividing 2 loaves of bread into 8 pieces and then trying to share it, and they're trying to come up with more problems to share. And then I'll tie this together with the sharing problem in a second. Mostly because I cheated and I already have it on the paper here, so I don't have to worry about stumbling with my English. So this is 1 over 8 plus 1 over 16 plus 1 over 24 plus 1 over 48, same pattern. And then the 2 over 9 guy is going to be 1 over 9 plus 1 over 18 plus 1 over 27 plus 1 over 54. So then they have all these decompositions. I'll allow you to fill in this table, but you can use this formula, and it shouldn't be too hard to fill in that table using that. We can go over that later. But now let's use this because I'm going to run out of time, and then I wanted to do geometry, and I also wanted to do an infinite arithmetic that they started getting from Bastet. No, is Bastet the cat? Yeah. It would have been Horus. The Eye of Horus, and the guy that he's fighting now. Set. Yeah. Because, yeah, we're going to get into it. Horus rips his balls off of Set. A true story. I didn't make the story out. That was the Egyptians. But then, because he's mad about that, he rips his eye out. I don't know which one I'd rather have ripped off. Yes, I do.
You have 2 eyes for a reason, right?
Yeah. It's like, you can take one of those. Okay, so some coffee. So now what we're going to do is go back to the question. Now that we see this decomposition a little bit, what we're going to try and do is we had all the 9 over 10. So the other column was writing n over 10 for all the numbers. So I'm going to take 9 over 10. If you actually look at the 9 over 10, this is what we're going to do is decompose it into its 1/2 plus, I'm just cheating because I'm lazy and I want to push through this. Yeah, plus 1 over 3 plus 1 over 15. And so from this guy and their analysis of this, now we can ask the real world connection between this. How can we share equally 10 loaves amongst, oh, that one was flawless, 9 people. Even I was surprised at how well that went. And then that'll be eventually the video game that we're going to try and push on everyone when we start this as well. This is Word World, or Land if we're in Mario, and this is Algebra Land. The power of algebra is it already looks a lot nicer, and once I have a decomposition and a clever, I use perfect numbers, or some wizard that was out there that didn't have TikTok or the internet a couple thousand years ago. He works out this formula and then uses it to apply it to the real world. And this goes to the person that was asking that question a couple weeks ago, whether I like applied math or theoretical math. Yes, but especially when you're teaching it, and to get more and more theoretical, the only way you can start down the journey of theoretical is with the concrete real world examples. So now what I would do is step 1. We can actually draw them first also. Was that it? No. Math is hard. There. Now I have 10. It's like 2 groups of 10. That'll be the next one. We're going to do heap problems when multiplying numbers using binary, which is awfully clever. Just a second. First of all, I'm going to take the first 8 and we're going to do halves. So take the first 8 loaves and half them. Take 1/2. Where are you going? I missed them twice. And so, or sorry, not 8. Oh, wait a second. Do you see what I did?
10 loaves.
Yeah, I dyslexic them. It's 9 loaves among 10 people. I was like, that can't be. I'm doing the wrong problem. This was 9 loaves amongst 10 people. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9 loaves. Yeah, so we'll take the first 5 loaves and half them. So then I've used those guys. Then what I can do is take the remaining 4. So I'm giving you, we're going to take them and put them into half. The step 2 is I take the remaining 4 loaves and split them into thirds. If you know how to split them into thirds. Split into 1/3. Then remember, I'm trying to do it into 10, so let's use orange. Those are the 2 left after I give them to 10 people. So first of all, this would 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The math worked out. If I take the first 5, I can give each guy half a loaf. So each guy gets a half a loaf. I'm assuming it's guys. You don't want.
Oh, yeah, I think the mic went mute. So,
Oh, my battery died.
Oh.
My battery might have died. Yes.
all right. Technical issues. Thanks for.
I'm gonna pantomime. No.
Thank you, viewers, for letting us know. We're switching the batteries there. We're still here. You can see Adrian walk around there a little bit. Is that one up and running? Were those batteries good, or did I give you bunk batteries?
Good to go. It says good to go.
Sweet.
Check,
Yep.
check, check.
All right, we are back. Thank
All right.
you.
I was like, what? I'm doing it right this time. And then you're interrupting me. It's like, I can't hear you anymore. It's like, okay, that'll allow. So each person's going to get this. And then can you see what we're going to do for the last one? Hint, hint. I'm going to take the last 2 blue guys. 3. We take the last 2 1/3 and split them into 5. Giving us 15. And so then everybody gets 1/15 also. I don't know how, I'm not drawing a 1/15. That's what he looks like. So that's how you split 9 loaves of bread amongst 10 people. Don't get it upside down. It looks like I made a face coincidentally.
Nice.
But this is one of the real world problems and why I liked looking at the history of math and why I jumped over teaching it even though I'd never done it before and I have no idea what I'm going to do, and you start in 2 weeks. Go. That's how it goes. Yeah, baptism in fire.
Your students never even knew.
They
Trust
never
me.
even. Oh yeah, that's his. And then once it happens, I'm glad that there's the real world and there's a couple students still around that do this because I make it look effortless. So does Connor McDavid, even if they lose. But they're practicing every day, all day, and that's the key to doing math and having confidence and getting up here and looking foolish because you keep permuting numbers because you have mild dyslexia and you can't spell worth the crap or form a proper sentence. I know that it'll come out right eventually. It'll work eventually and I can get my meaning across, but I'm going to be confident in what I do, and math is the one area where you have to be, you can be confident in other areas and bull crap your way all the way through it. But with the math, Femvox fan will keep saying, isn't that a negative? It's like, shut up then, I guess. So there's a way of checking with the math because the formula should work out eventually.
The
So,
Sign Patrol. The Sign
Yeah.
Patrol. Yeah, and according to some sources, they did cut their bread like this to share equally, at least for demonstration purposes. But not too sure about that one. What do you think?
yes, so this is where back in the day, I wasn't there 2,000 years ago, but it's,
5,000. 5,000.
I guess it would have been, yeah, when they're doing the Giza, when they're at the time. Yes, most likely, I'm going to guess no, they wouldn't. They would do it the way that I would do it. They would just chop it up into the pieces, and then the piece that was left over, I eat it, and then none of the kids get the jelly. When I divide the jelly beans, whatever, if there's 3 jelly beans left over, I eat those, and then that rectifies it. But it gives a good practical way of saying, why would I want, what we're trying to do is analyze backwards if we're talking about the history. I just am interested in the math that it works out. If I have a real world problem where I have to solve n things into k people, then we have this way of decomposing it and getting strange amounts. You could probably do it different ways and share them in different ways, or just if you're trying to make it equal, just cut it into the closest piece and then throw away the little piece, or throw that into the bundle for the next loaf of bread. I have no idea historically, nor do I really care so much about whether they were actually doing these things. This is where you'll start seeing where the mathematician comes out of me and not the historian. Well, all I wanted was to give you a seemingly real world problem that would give rise to why they would want to have fractions of this form. Because now if I wanted to take 9/10, and why they all wanted them unit fractions, I don't know either. But if I want 9/10 of something, I know that I can decompose it into this, and it gives you a real world problem of saying you get 1/2 of a loaf, 1/3 of a loaf, and 1/15 of a loaf. And then in there, it also gives you a way of showing that to link the algebra and the real world problem, you still have to logically step out and give a process of how you're going to obtain the 1/2 loaf, 1/3 loaf, 1/15 loaf from the whole 9 loaves of bread. Because in there, what we did was we actually multiplied. In this one, you can notice that this is actually, why did that work? Because you're actually taking the 1/3 times 5, and that's what we did in the last step. You took the 1/3 and split it into 5s, so that means you get 1/5 of a 1/3. And that's how there is still a little bit more to be said to doing the real world practical application and then just having abstract nonsense written on the page. And this is what I'm trying to enforce, is that the abstract nonsense on the page comes from a real world problem, and you should practice linking the algebra to what you really want to do in the real world. Otherwise, you're just chasing your tail and doing education where they just told you to do these computations, and then you're just running an algorithm and have no idea why you're doing it. So that's what I'm trying to flesh out here. Yes, they did do it exactly this way. You're never going to get me to answer that way. I have no idea, but I'm going to guess, and it suspects from even this, from the Rhine papyrus, we do have actual evidence. This is a copy of one of the Rhine papyruses that has a bunch of geometry in it. But they were definitely doing these types of things. And then in the writing, this is from the real papyri. This is exactly what they're trying to say in the problems that they have written down. So taking them directly from the Egyptian sources, yes, it seems like they themselves wrote out the problems this way and showed solutions using these unit fractions on how to divide 9 loaves of bread into 10 people. And so yours is, how do you take, what's the one that I gave them now? 3 loaves of bread into 5 people. Use the unit fractions to start practicing this. Yeah. Okay,
and
good.
then post your solutions on the Discord.
Oh, on the
link is
on the Discord. Just wait.
earlier on in the chat. So
Let me
be sure
find
to
my
join
other
us
stuff.
there, and you can definitely post solutions there. We'll take a look.
Where's my other stack of paper? Oh, I don't need that one. Now I need this one. Okay. Now we'll switch gears. We're doing more than half an hour, I think, possibly. Is that all right with everybody?
We are already past half an hour.
Okay.
Half an hour is in the rear view mirror, so keep going.
Time flies when you're having fun. We get to do aha problems. Take on me, take me. So these are heap problems. Or I believe what the Egyptians actually called it. Let me double check. Oh no, that's the Imes one. We're going to do that one. Oh, we'll do the heap ones after. This one is successive doubling. So what we're doing is multiplying numbers together. Remember, this is at a time when they just barely had learned how to press papyrus into sheets that you could write on. So they don't have, the average person doesn't have a booklet they can go in and start practicing their homework in a tablet or in a piece of paper because it doesn't exist. They don't even have paper the way that we know it. They had reed papyri that they had glued together in a form, but I'm going to guess only the priests or the aristocrats are going to have this, the pharaohs. So they don't have this, so they need a way of multiplying numbers together in their head or with pebbles, etc., and having an efficient way of doing that. So let's learn by rote. That's where Lorenzo learned the word rote was from me. So let's multiply 3 times 6 using duplication. Which I thought that was quite clever. And so what we're going to do is first we take the first number. Where did my Euler's blue go? Oh well. We're going to take the first number 3, and then we're going to take the second number, and then what we're going to do is we're going to do powers of 2 in the second column. They're using actual heaps. The heap comes from they're using rocks to gather this together. And then what we're going to do is we're going to successively double the number. And then for the first one, this is 3 to the 1. So they're writing this as 1, which is 2 to the 0. They didn't have algebra this way. I'm just going to write it this way in the modern form to show you. Then this is 3. 2 times 3 is 6. And so then this is that's in the wrong spot. 1 multiple of 3, which is the same as the other one, but it's okay. This is 2 multiples of 3. So this would be, wait, I'm doing it wrong. I'm doing it wrong. Luckily I have this. This is 3, which is the first multiple of it. This is 6, which is the second multiple. This is 9. No, I'm doubling the number. Double the number each time. 6 times 2 is 12, and then 24. And then what we're going to do is double the number, so we're going to get 4, and then we're going to get 8. So we do get the powers of 2. Then what I'm going to do is, cleverly, now that I've got it on the board, and you could delete that, what I just did there, trying to be fancy pants. What you do is, it's extremely simple. You take the first number in the multiplication and you successively double it. I don't know where you stop per se, but there's probably an algorithm I can figure out where we would stop. But list the first, I ran out of the board, and this will be convenient for us anyways. And then what I'm going to do is, I'm going to take the second number now and decompose it as powers of 2. So now I know that 6 is 2 plus 4. And so what I'm going to use is this one and this one. And then that will give me 6 plus 12, which is 18, which is the multiplication of 3 times 6. And I used a baby example with some fairly small numbers to show how it works. But for extremely large numbers, not having calculators or paper or anything to write this down, this became extremely useful because they're just going to use the powers of 2. So again, what do? I take the first number, I successively double it in the first column. Then I write down the appropriate powers of 2 next to it. Then I take the powers of 2 and decompose the second number, and then the columns or the rows that had the powers of 2 in the first entry are going to add to give me the outcome of 3 times 6. If you didn't like that, unbeknownst to you, you've been taught through K to 12 how to multiply numbers together, and there are, unbeknownst to you, more than one way of doing this. Once we get to India, I'm going to give you another way of doing this, which is even more clever than the other ones, than this one. But this one, just using doubling of numbers and the binary, you can get multiplication of all kinds of numbers. And then what's the last one I want to do? The last thing I wanted to do here was, yes, we have to draw the Egyptian Eye of Horus. It's Horus, right?
Yes.
Set was the one that was the bad guy. So now can I draw this fancy pants? Oh, and then we have to get which pieces were going to be which. Okay. There's his eyebrow. And then what did I want? Then he wanted this guy. And then I've got one more, which was this guy. Close enough. So this is the Eye of Horus. What they would do was they're taking this, and then let me do, what did they call it specifically? All right. So they called, without that in there, they're going to call this 1/2. No. I guess it looks like you just started over here. This is 1/2. This is 1/4. This one is this one's 1/8. This one's 1/16. What else do I have? 1/32. I'm just copying the picture that I stole from the internet from this business. But this is, again, what the Egyptians, I think, specifically were calling these pieces. Now I can tell the story, and then we'll see where we get what's happening to this. Do you see what's going to happen? We're going to get to this eventually. Which is what you have to be careful with this one. Now I'm already doing something else before I tell the story. How do you change this in index shift? I want m to be n minus 1. So then n is, no, I want.
Should the index actually be 1 instead of 0?
Yeah, oh, so that's what, yeah, exactly. But if I take one of those off, what do I get? The sum from n equals 1 to infinity of 1/2 times 1/2 to the n minus 1. Yes. Okay, I'll write it the way that you want. The sum from n equals 1 to infinity, but it has to be 1/2 times 1/2 to the n minus 1. The formula is this. Yeah, that's why I had a problem. It's n equals 1. Lorenzo's correct. The disembodied voice is correct. But then it's q to the n minus 1, whatever the quotient is. We have specifically, I stole a step. We want to start from n equals 1. So I wrote the 0 down wrong. But this is going to be 1/2 to the n. But to run the formula, you'll get it wrong if you try to do it, which will be, now I'm just going to split this as my favorite dirty trick, minus 1 plus 1, and I'll take the half off. So this will be the sum from n equals 1 to infinity of 1/2 to the n minus 1 times 1/2. And the 1/2 I can take to the outside. So this one will converge, but it has to be of that form. Yes, you're correct. Because you're going to get 1/2, and then you'll get, what will you get? This is 1/2 over 1 minus 1/2. Do you see? Which is exactly 1. If you know what you're talking about. How does this connect to this is what you're asking, hopefully, probably. So then what we're going to do with this is, the story is Set and Horus have a fight, and they rip off certain body parts of each other. In this one, it is Set takes his eye and rips it into 6 pieces. The first powers of 2, and each time he rips the eye apart, he rips it into half again, or 1/2 smaller, something like this. It was the words that are going to say this. So he splits it into fractions of a 1/2 piece, a 1/4 piece, a 1/16 piece, a 1/8 piece, a 1/32, and a 1/64 piece of the eye, and he scatters them across the land, so he'll never be able to put his eye back together, and then he'll have no sight. And so what they realize is, when they go say, they thought theoretically that they could put the eye back together and put it Humpty Dumpty back together again, But when they go to put Humpty Dumpty back together again, they realize that they get a 1/2 plus a 1/4 plus a 1/8 plus 1/16 plus 132 plus 164, which is going to be a finite sum. What's that going to be? It's going to be the sum from n equals 1 to, what do we get? 6. This is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6 of 1/2 to the n. So it's the sum, but it's a finite sum. But what they realize is what happens when you add that up. When you get the common denominator and multiply everybody by what's missing, 32 over 32, and then we're going to have all the way through, and then this one I multiply by 2 over 2, you can spare you, but when you get that, what do you get? When you add that up, you get that this is exactly 63 over 64, so 1/64 is still missing. And so then this bothered them. No matter what they do, if they do this, they're like, well, what are you doing here? And what's going on? The only way that you're going to get unity is if you had an infinite sum of these fractions. And then this is how you get one of the first early things of going from a finite sum to switching to an infinite sum to get the unity that they wanted. So I thought I would point that one out quickly. Maybe I'll describe that a little bit better next time. But I'm already rushing because I wanted to end the stream in a reasonable amount of time and talk about the geometric considerations.
All right, so we're going to take a quick break here. We're going to stop the stream and restart it in about 5-10 minutes. Thank you, everyone. We'll be right back.